welcome everyone back from our break here at 3:40. Next up, we have Amalaye Oyake of Blue Origin, another longtime friend of the Flight Software Workshop and past committee member, presenting Space ROS, a framework for space robotics. All yours.
All right, afternoon. So this presentation is Space ROS, a framework for space robotics. And I want to give a few acknowledgements to individuals who have helped and contributed to this work, particularly Will Chambers at Blue Origin, Kim Hambuchin at NASA, Matt Deans, Brian Roberts, Rob Effinger, Dan Burns, John Lum, and also Paul Tompkins. So I will share a little bit about what Space ROS is. And so Space ROS is a collaboration between Blue Origin and NASA, along with Open Robotics. And it fits in line with the mission of Blue Origin. So at Blue, our goal is to build infrastructure in space. And so the plan is to have people living and working in space to benefit Earth. And a big part of this is enabling affordable, reliable access to low Earth orbit and also lunar orbit as well. And so New Glenn is pretty much our highest priority objective right now, just working towards our first launch. And so we're working towards building up the infrastructure that will take advantage of the New Glenn rocket as well. So New Glenn is our first step. And so I am part of the Advanced Development Program group, and some of the things that we're working on are reusable space transportation. So New Glenn is a big part of that. We have a lunar objective as well as space mobility, and we recently announced the Orbital Reef space station. And all of these are active endeavors that we are working on. So from low Earth orbit to the moon, we're actively working on capabilities in all of these areas. And so with robotics, robotics forms a really big part of building infrastructure and capabilities in space. And so Blue partnered with NASA to mature the ROS2 framework and make it suitable for spacecraft flight software. So we announced a collaboration with NASA, and the collaboration involves NASA, Blue Origin, and Open Robotics. So some of the team members are Will Chambers, who's the principal investigator, as well as Matt Deans, co-investigator, Brian Roberts, Kim Hambuchin, and also we have a lot of other contributors as well from Open Robotics. And Paul Tompkins was a key part of this. He was the mission architect. So Space ROS really leverages this collaboration to create essentially an open source framework. So I'm going to get into a little bit about what we're doing and where we are. And so as part of our collaboration, we published an RFI, and we got a lot of responses. We got quite a number of responses, and we hope to review the responses and take advantage of some of the suggestions. But I do want to say that even though the RFI deadline has passed, we're still open to receiving input. So if you go to the link and you go to sam.gov and find the RFI, you can still send messages and responses to the RFI. So you can still respond, and we will still look at the responses. Okay, so let me get into this and talk a little bit about space robotics. So as we look at NASA roadmaps and project roadmaps, we see more and more ambitious missions being planned in the future. And you see a lot of different technologies being deployed on planetary surfaces or orbiting another planet, or going into deep space to do exploration. And these capabilities or future plans will require some form of robotic capability to enable to assemble structures or to do autonomous exploration of planets or moons or various kinds of functions that would require a high level of autonomy. So space robotics are a big requirement for the future of space and the things that Blue Origin and commercial space companies are planning to do. So as I move on, the rationale really for what we are trying to do is build a framework for space robotics. So if you look at the current software frameworks that exist within the flight software community, you see the core flight system, you see F prime, but there does not exist a space qualified framework for robotics. And we've seen the area of robotics grow tremendously with the Mars rovers and other robotic missions, some that have been presented here at this conference. And so what we envision is really a framework that can replicate the success of CFS, that will provide a library of robotic functions and applications that software developers can use to develop their software. So I talked a little bit about the core flight system. And so if you are a longtime attendee of the Flight Software Workshop, you will remember when CFS was first presented many years ago. It was presented as an OSAL layer, the operating system abstraction layer. And it slowly grew from that to CFE into the entire framework of the core flight system. So CFS has seen a lot of success. It's the most common spacecraft flight software framework, and it has been very successful. So what we are trying to do is learn from the lessons of CFS and take the ROS2 framework and mature that framework to make it suitable for spacecraft flight software usage for space applications. And so the idea is that we would mature the ROS2 framework, but the plan is not to replace existing frameworks like CFS or F prime, but to develop a framework that would be suitable for the development of robotic applications. So you could have a robotic application that could exist as a subsystem, or you could have a robotic application where the space ROS framework would control the entire robot independently. And so, as I mentioned, Space ROS is a framework that we are actively developing in collaboration with NASA. And the intent is to develop a framework that meets several key aspects, namely meeting mission and safety assurance goals, benefiting from the existing code base of Space ROS and ROS2 to reduce cost and schedule, to enable a better software integration and software interoperability. And a big goal that we are shooting for is compatibility with ROS2 applications. Some of the other attributes that are very important are the real-time and deterministic requirements for space missions. Space missions require very rigorous quality assurance requirements. And this is a very big aspect of the Space ROS development. So we really want to benefit from, by maturing the ROS2 code base and maintaining the open source nature of ROS2 with Space ROS, and make the software much more robust and more suitable for spacecraft flight software, so that developers who are developing robotic systems can use something that they are familiar with, because the Space ROS API would be very familiar. It would be essentially the same as ROS2. So I talked about the growth of space robotics and the demand for robotics in space. If you look in the sort of the space ecosystem, you see a wide array of robotic systems, from rovers to manipulators to robotic systems that are part of landed assets on the surfaces of moons or planets. And so our goal is that Space ROS would be applicable to the wide array of robotic systems that are being deployed in space. And this was a picture that was put together with the help of Paul Tompkins, basically doing a survey of the different kinds of robotic systems that exist today. So we're very familiar with the systems on the ISS. There was a Viper talk today, but there are other systems, such as systems that help retrieve assets from lunar landers, cranes, humanoid robots, and also autonomous landers and other free flyers. There are lots of different kinds of robotic systems that we can imagine and that are needed for space missions. So at Blue Origin, one of the projects that we are working on that I mentioned is the orbital reef. And a part of the orbital reef involves several robotic functions. There is a single person spacecraft, as well as a manipulator as well for various robotic functions that would be a part of the orbital reef. So orbital reef is a commercial space station that incorporates a space tourism aspect as well. And so there will be science as well as space tourism that will be part of the usage of the orbital reef space station. So as part of Space ROS, what we did is we built up essentially what we call a robotic and autonomous systems technology taxonomy, which tries to capture the various technology aspects that are required and needed for space robotic systems. And so we built up this very big categorical list of various functions. And our goal is to try and identify the various software components and subsystems that can satisfy the needs of these various areas. And so this is an aspect of the Space ROS work, trying to provide the functionality and capabilities for the various areas that are required for space robotic systems. The first thing that we're really starting with is really the safety critical software design. So I mentioned that we are maturing the ROS2 code base and improving the quality and robustness of the ROS2 code base. And so a part of this is implementing code quality guidelines and code software improvements to the ROS2 code base to mature the various aspects of the underlying C++ code. And so we recognize that a robotic subsystem may be deployed in various ways. It might be tightly integrated into a flight computer, or it might exist as a separate unit, such as a sort of an LRU or an integrated modular avionics system, completely separate from the flight computer. And our design of Space ROS is to embrace the diversity of robotics, the diversity of ways systems can be deployed on a spacecraft. And so as we are developing Space ROS, we want Space ROS to essentially be flexible to the way people might deploy systems, but more importantly, we want to make sure that we are aligning with space industry software quality standards, so that software developers will be able to satisfy the requirements of the various gated reviews, such as your certification of flight readiness and your CDRs and whatnot. So I talked about software quality standards and specifications. So there are many of them within our industry. There are NASA standards, DO1. There are other standards such as DO 178C, ISO 26262, which is an automotive standard. FACE was mentioned in the RTEMS talk, and a big part of qualifying code is making sure that your code passes static analysis as well. And so the various tools output various formats in terms of the reporting files that they generate. But more recently, the SARIF standard has been created to sort of standardize the output of static analysis tools. And so this is a standard that we're looking at to integrate with the Space ROS continuous integration system. So Space ROS is more than just a framework. It includes a continuous integration system, and we use the term continuous qualification. And what that means is that the framework will run through the continuous integration pipeline, but it will also aim to automate the qualification process as well. And so as a part of this is that the system will generate artifacts at every step of the build or the unit test or the static analysis process. So I will show that, show a little bit of that in a picture. And so what we're trying to do is provide a system that automates the software qualification process. So what that means is that the software requirements for a project that would be using Space ROS would capture the requirements in the normal way in a table. But in addition to this, what we will do is provide a tool that will enable software developers to rewrite the requirements in a formal language. And that tool that we're using is the FRET tool from NASA. So with the software requirements, you would have your requirement ID, your requirement text, your rationale, and an additional column, which would be the software requirement text rewritten in a formal specification. You would have your normal software development process using the framework, but we would run compliance checks against various specifications such as MISRA, AUTOSAR, DO 178, and others. All of these steps will produce artifacts at every stage of the process, and you will be able to visualize the generation of the artifacts through the continuous integration process through a dashboard. And so what we are building is not just a framework, but we're building essentially an automated continuous qualification system alongside the framework as well, that will comprise of unit testing, automated testing, as well as checking of the software requirements themselves. So one might ask, how does one automate the software requirements check? And so I'll explain that a little bit. The idea is to automate the test procedures. So typically test procedures may be written as a Microsoft Word document or a spreadsheet or a PDF document that someone would manually sort of go through in a test bed. Our plan is to use a Jupyter notebook and automate the commands that are generated and checking against the telemetry responses from the system under test. So I said a lot there. I'm going to walk through the rest of the slides pretty quickly because there's a lot of material. So some of the code quality aspects that we are looking at are coding style enforcement, MISRA rule enforcement, power of 10, static analysis rules, and essentially passing unit tests. So tools that we are employing our Flaw Finder, ICOS, CPP check, Clang, Cobra. There will be a Cobra presentation in the flight software workshop, and we're also looking at other tools. So the idea is to use open source tools as part of the Space ROS continuous integration system that we're releasing, so that users will not be required to purchase licenses. Okay, so how are we improving ROS2? Okay, so this is really the meat of the talk. What we are focusing on are the C++ layer, the ROS client libraries, the ROS middleware layer, and looking at other underlying middleware applications besides DDS. So the intent is to the timing and logging functions in the C client libraries, impose good quality rules from the top to the bottom, and explore more different middleware solutions for the middleware interface. So I will speak to this a little bit. And along with the middleware development as well, we are also looking at making sure that Space ROS can bridge with other frameworks such as CFS or F'. And this is a very valid use case for the use of Space ROS, bridging with other flight software applications, which may be the primary flight software application for a spacecraft. So getting a little bit deeper into this, we are also looking at two specific ports to RTEMS and VxWorks. Right now, our Space ROS initial development is targeting Linux. Okay, so I mentioned a little bit about the ROS middleware layer. So ROS2 is designed around DDS, and DDS is very well supported. I think one of the main issues is that Eclipse Cyclone DDS is not spacecraft flight software. RTI Connects DDS is approved for space vehicles, and that's in use, I believe, on Orion, and I think it's baselined for Gateway as well. But what we are looking at are usage of C2MS, looking at bridges and message passing over a CFS software message bus. And we are specifically looking at the CCSDS, asynchronous message service. And AMS is very promising because it is designed for flight software use. It's similar to DDS in very many ways. It's open source, and it's scalable across vast distances. So you can do pub/sub across low Earth orbit or millions of miles away. So I've used AMS to send messages to a spacecraft 25 million miles away. I did that as part of the Epoxy DINET project, and that was a very successful technical demonstration of pub/sub across deep space. And so we're working on a AMS integration with Space ROS. Another aspect of the Space ROS work is people not having real hardware. Right, so we are looking at the concept of digital twins, and what we're envisioning is a software-defined spacecraft. And so one might ask, how do you intend to do this? There are open source technologies that enable this sort of thing. A particular technology is Renode. So Renode is a tool like Symix, which allows you to run your flight software on a simulated target. So I've run RTEMS on Renode. Actually, I did that just last night. And I ran it against a simulated Leon 32 platform, and it worked. The compiled code worked as if it was running on real hardware. It was quite interesting. So,
1 minute warning.
Okay, thank you very much. So, in summary, Blue Origin is actively developing Space ROS in collaboration with NASA and Open Robotics. We currently have a private GitHub repo that we will open up very soon, when we announce the minimum viable product, and Space ROS will remain open source. At this point, I can take questions.
Okay, I think we have time for one brief one.
Okay.
So here's a question. How do you balance the open source super varying code quality character of a code base community like ROS with the needs for safety critical flight software?
Right, and that's a really great question. So what we are doing is we're employing essentially a battery of tools to essentially generate all the various issues that we expect to see in the ROS code base. So in the current private repo that we have running, we're actively doing that. And what we will be doing is essentially making code modifications to the ROS2 code base to drive down the number of issues that we are seeing, and we do see a number of them. So dynamic memory allocation, exception handling, a lot of these things we're going to eliminate. And that's what I can say. I can answer more on the Slack channels, but this is something we're actively doing.
Okay, wonderful. Thank you. And we're out of time, and we'll move the remainder of the questions over to the Slack. Thank you so much.
Thank you very much.